Okay, so we've got this guy who always swims at a certain angle. How about let's have him swim at north 60 degrees east. He always heads off that way and he's swimming along in that direction. And what's a reasonable swimming pace? 3.6 kilometres per hour. That's the velocity that he swims at in that direction. So say we've got a river that is 300 metres wide. How long is it going to take him to cross the river? So let's have a bit of a look at the situation. This guy, he heads off in a direction of north 60 degrees east. And he heads off at 3.6 kilometres per hour. That's the direction he always swims. And we want to know how long it takes to cross a river that's 300 metres wide. And we're assuming that the river is placed like this. He starts off on one side of the river and he ends up on the other side of the river. Okay, so this river is 300 metres wide. How long is it going to take to get across there if he's swimming at that angle and at that speed? So there's a couple of things we need to know. Of course, we remember what our equations are. For example, speed equals distance over time, or the various versions of that. Now we want to know how long something's going to take here. So the version we're going to be after is time, the distance over the speed. Now, what is the distance? Well, given that the speed is in kilometres per hour, I might keep it in kilometres for the time being, and the answer in terms of time will come out in hours. And if that's unreasonable, I'll convert it to minutes or whatever. But at the moment, we have a distance of 0.3 kilometres. And the speed, that's the thing that we've got to work out here in terms of the vector. So we need the speed that's going in that direction. But they've given us the speed at the angle north 60 east. So how much of that blue vector is going in that vertical direction? That's the question. Because that's the S that's going to go underneath here. What is that speed? Well, you could use just straight trigonometry if you want to figure out what that is. Either you can work that that's 30 in there and say that sine of 30 is equal to S on 3.6. So S is equal to 3.6 sine of 30, or you might have already done it and gone, well, no, I would say it's 3.6 cos of 60 because I'm using cos is that on that. So you could use a straightforward trigonometry if you want to. And that time is going to work out to be 0.3 divided by 3.6 sine 30. 0.1666. 0.1666 what? Well, the speed is in kilometres per hour. So the kilometres will cancel. H to the minus 1 is just H. So that's how many hours. If you press this button on the calculator here, it tells you it's no hours, 10 minutes, and no seconds. So basically, it's going to take 10 minutes to cross the river under those circumstances. If nothing affects him and he just swims straight across at that angle, a 300 metre river. But what if he encounters some sort of water flow in the river? So let's have the same situation as before, north, east, same river, 300 metres wide. The guy always swims in that direction at 3.6 kilometres per hour. He's always swimming in a north 60 degrees east direction. But now what happens is we have a river flow. The water is flowing that way. What would river flow at? Maybe 8 kilometres per hour. The river's flowing that way. So you have him swimming that way, but the river flows in that way, pushing him along. But he still always heads in that direction. When he's swimming, he's doing that. But of course, he's being pushed that way. So we're going to want the resultant vector of that. We still want to know how long is it going to take to swim across that river. What I'd like to do is write his vector in component notation and also write the purple vector, the river flowing, in component notation to start with. So his vector, this one here, which is his swimming vector, would be in this direction, say that, I'll just write 30 degrees in there. Going this way, it would be 3.6 cos 30 degrees. Now, what am I saying is I? Well, I'm going to say that the easterly direction is the x-axis and the northerly direction can be the y-axis. That's just pretty normal. So he's swimming at 3.6 cos 30 in that direction, and in that direction he's swimming at 3.6 sine 30 degrees. Now, if you wrote sine 60, cos 60, you'd still get the same thing if you wanted to use that angle, but I'm just used to using the one with respect to the x-axis. So I've written it in component form. And if I write the purple vector in component form, it's no garbage. It's heaps of I, it's no j. How much I is it? All 8 kilometres is heading negative I. So I can fix that. It's minus 8I plus nothing in the j direction. So if I look at the resultant vector for that, I'll call it R, the resultant of what's happening. His blue swimming that way and the purple current flowing that way. I add up the x components, and I add up the y components, plus nothing. So that's what I get. This works out to be 3.6 cos 30 minus 8, about minus 4.8823i. Sine 30 is a half, so that's 1.8j. So the result of him always swimming that way, but the water always coming in directly there from the left, is that's what the velocity is going to be. It's going to be actually a vector heading out to the left and upwards. That makes sense because we've got a vector going that way for the way he swims. We've got a vector going that way for the way the water's flowing. So the result of them, when you add them together, is going to be a vector going that way, which is the one we've just described. And if I just draw these back in here quickly, this resultant vector, we can work out what its magnitude and direction is. So I'd like to do that now. The magnitude and direction of that resultant vector there. So I can just push that up a little bit more. And we can see that at the top of the screen. So the size of this vector is the square root of the x component squared plus the y component squared. So I've just got to square that, plus 1.8 squared, and then square root that. It's about 5.2, I'll just say, and we're talking about velocity. So resultant is 5.2 k's an hour. He was only swimming at 3.6, but there's 8 k's going that way. So altogether, 5.2 k's an hour in that direction. What direction? Well, there's various ways you can answer the question about direction here. From the positive direction of the x-axis is going that way is quite common. You could just point out what that angle in there is. You could go around this way, from the north all the way around to there if you want a true bearing. And look, bearing in mind that we do have a north and an east in our question, we are referring to those directions. I think I might give the answer in terms of north, south, east and west. In which case you always go north or south first and then east or west second. So the angle that I'm interested in is that angle there if I want to give a bit of direction to that. So what is that angle there? Well, we know that going out that way, you would be going up 1.8 because that's the y component of it, and you'd be going across 4.8823. So you could work out that tan of theta is 4.8823 on 1.8. So shift tan of 4.8823 on 1.8, and we end up with 69.76 degrees. So the total of what's going on here is that his resultant vector is 5.2 kilometres per hour north, 69.76 degrees west. That's what's happening overall. Okay, that's a good discussion, but we've got to find out how long it's going to take him to cross this 300-metre river under these circumstances. He's trying to cross this 300-metre river, and he's swimming in a direction like that at 5.2 kilometres per hour, and his direction is at 69.76 from the north to the west. So how long is it going to take him to cross the river? We need to know what his speed going that way is, because that's the crossing of the river. You can swim as far as you like down that way, but you're only going to cross it if you're going that way. So what component of his speed is going that way? All right, well, we already know it because we've got it in component form. We know from the work that we did before that the resultant vector is minus 4.8323i and 1.8j. So we know that it's 1.8 in that direction. So if the vector we're talking about is 4.8823 in the x direction, negative, and 1.8 in the y direction, then there's 1.8 heading up there, 1.8 kilometres per hour heading in that direction. So, like before, we're trying to find the time, and we said that time is equal to the distance on the speed. So it's equal to the 300 metres across the river on the speed, which is 1.8 kilometres per hour. We're going to do everything in kilometres, so it's 0.3 on 1.8. And 0.3 on 1.8 is 0.166 kilometres per hour. No hours, because kilometres will cancel. You have h to the minus 1, which is h when it's on top of the fraction. And that's 10 minutes. Does that surprise you that it's taking the same amount of time to swim, even with the water flowing across? Well, it shouldn't surprise you, because if the water's flowing across, as in this diagram up the top here, it's only pushing sideways. And with his original motion in that direction, he's still going with the same speed across, whether he gets pushed down that way or not. So it's still going to take the same time to cross the river, whether that water is flowing in that direction or not. In the next question, we might change the direction of flow, and then the time might change.